So I was chatting with Howard Hinnant about ideas for a talk like this, and he suggested the name Moving Faster, so thank you, Howard. He also told me a story. His wife, Teresa, can type 90 words a minute, which I gather is kind of par for the course for a professional typist. Sounds scary to me, but... And 30 years ago, her computer could keep up with her. So let's look at that a minute. 90 words a minute is 450 characters per minute, right? 7.5 characters a second. So 30 years ago, I had a Mac 2 on my desk. Had one thread running at 16 megahertz. So let's see. That's per character 2 million instructions, right? Per character. Of course it could keep up. You can do a lot in 2 million instructions. So we got frozen for 30 years, and they've just thawed us out. And now it's 2018. Well, I just bought this thing a couple of months ago. And it's that. It's got 8 threads running at 2 gigahertz when it's calm. It goes faster than that. So what's that, everybody? 2 billion instructions per character. So you all know where this is going, right? Howard's wife, Teresa, her computer today doesn't keep up with her typing. What are we doing wrong? I mean, that's ridiculous. Well, I don't know all the answers. But here's some things that I think that we might be doing wrong. And I'm going to talk about some specific things that maybe we can do better. So when does efficiency matter? Typing, really? Seriously? The world record for typing speed, according to Wikipedia, is 216 words per minute. Set by this person in 1946 on an IBM electric typewriter. That was pre-Ball, not a Selectric, okay? Computer can't do that? I mean, and over the last 30 years, 1,000 times increase in speed. I mean, sure, we're doing more, but are we doing 1,000 times more stuff? Well, there's a lot of reasons for this, and I'm only going to talk about some of them. But I want to give you a couple of examples, though, of when efficiency matters. The company I used to work for, they hired me to work on a program that extracted data from their database and made a product with it. This is a digital map company, so their data was pretty big. And their system took 3 weeks to run. And one of the things they wanted me to do was make some intermediate stopping points so that, if something went wrong, they didn't have to go back all the way to the beginning of the process. Well, I didn't do that. I rewrote it to run in 5, maybe it was 8, something like that. Anyway, overnight, about 100 times increase. I mean, this was a game changer business-wise, as you can well imagine. The current company I work for, we have a test automation system for our rail simulator. And 2,700 tests we have at the moment take about an hour and 10 minutes to run today. We're rewriting it, different design, reducing that to about 20 seconds. So that's also going to be a game changer for test-driven development. So my point here is that efficiency matters. Efficiency always matters. This kind of efficiency is something that you can get, I mean, this kind of efficiency change is something that you're going to get with design changes, which is not what I'm here to talk about today. But once you've made those big design changes, now all of a sudden your code is running much faster, and now the bottleneck may be things that aren't so obvious, subtler things in the implementation, and that's what this talk is about. So where does efficiency matter? The rule of thumb that I grew up with was don't optimize your code. Write it the nice, clean way. Go find the 5% of the code that's spending 95% of the time and fix that. Well, you may throw things at me, but I don't think that's the whole story. I think that's necessary but not sufficient, and I think that there are many programs that do not spend all their time in a small bit of code, and that if you write a big, huge program without thinking about a performance anywhere, you'll end up with a big, huge, slow program that you can't really fix. Actually, the rail simulator is an example of this because if you run it with the electrical traction power simulation on, it actually does spend almost all of its time in a very small bit of code. But if you run it with the electrical simulator off, it actually spends its time all over the place, and there's no one spot that you can fix. So I say write almost everything optimally. But optimized code is ugly, right? I think in C++, optimal code can be elegant, and that, in fact, optimal code is typically the most correct code, and so therefore, kind of by definition, the most elegant code. I think that our idioms should be for optimal code. And our idioms are kind of by definition, the elegant way to do things. And if something really ends up being ugly, you can hide it in C++ behind a very elegant zero overhead abstraction, often. This is done in the standard library. In fact, the date-time library does this all over the place. Matrix arithmetic libraries do this. So what about compilers? Well, compilers today are very smart, and they can't fix design problems. That's pretty obvious. But they also can't get around all coding inefficiencies. They'll fix that, right? Don't have to worry about that. But they won't fix this, and we're going to go into this and what's wrong with it. So I grew up with simple architectures. I didn't know what a cache was. Floating point was super expensive. This was back in the old days. All right? The golden rule used to be reduce FP divides. Count your FP divides and get those down as far as possible if you wanted your code to go fast. Well, floating point's faster than integer now, or certainly as fast. I didn't actually realize that until not that long ago, when I suddenly did some experiments and realized, wow, you know, this rule that I've been holding in my mind, it's just not true. So caches are big, and they're much faster than main memory, but they're not big compared to main memory. And the faster they get, the smaller they get. There's more than one, right? So locality of reference is critical, which means that size matters. The fact that you've got 32 gigabytes of RAM doesn't mean you can just arbitrarily write huge code, because it won't perform because of caches. So cache misses are the new floating point divides. So theorem 1, avoid cache misses. Dynamic allocation. Heap allocations are the most expensive things we do. I mean, if we're not talking about going out on the internet for something. And deallocations are the second most expensive. So we need to reduce these as much as possible. We need to count our allocations. Don't worry about counting floating point. Count our allocations. Reduce them ideally to 0. Can't always do that. Standard containers, they use heap allocation. But heap allocations are not only expensive, but the locality of reference is terrible. They're all over the place, right? So there's a double whammy. So theorem number 2, avoid allocations. The stack, on the other hand, is contiguous, so it has great locality of reference, and it's used constantly, so it's always in cache. So if something isn't too big and it's local, it should be on the stack. No reason to put it in a heap. Nothing's faster than a register, right? And so the compiler's going to try and put things into registers. There's lots of them. It's going to use them. In fact, lots of variables are only in a register ever. But if you take the address of a variable, or of course if it involves dynamic allocation, it's not going to be only in a register. All right, so that, and by the way, I didn't mention, but interrupt with questions anytime. So those are some basic principles. Maybe most of you already know these things. Let's talk a little bit about embedding objects. So size matters, and locality of reference matters, and dynamic allocations matter. So you've got a contact object. Do you implement the phone numbers as a vector or as an array? Well, it's a trade-off, right? If you do it as a vector, you're going to end up with 2 different allocations and bad locality of reference. If you do it as an array, well, you've got a limited size. And array doesn't actually have a size, so you're going to have some way of putting phone numbers into it and telling that the rest of them aren't valid. So this is your situation. But this lower approach has the potential to run an awful lot faster. We don't today have a fixed capacity vector or a short string optimization. What I call an SSO is probably really a short buffer optimization vector. Both of these are ideas that are being floated for the standard library, but we don't have them today. This would be a perfect case for the short string optimization, right? Because you usually just have 1 or 2 phone numbers, and sometimes you've got 10. Well, we can go better, right? Embedding objects. What about if we embed objects on top of each other? How can we share space? Well, unions, in C++ 98, unions were kind of useless. You can't really put anything in a union that means much of anything. That got fixed in C++ 11, so you can use unions. They're quite useful. They're still dangerous. If you write one thing and read another, you're doing undefined behavior. Don't do that. But you can really save space, and that saves time. But unions aren't really ever safe, so also in C++ 17 we have variants. A variant is a safe union, and they're great. You should certainly use them. But they add some extra space because they have the type tag. So you can't, for example, save 4 bytes when you want to superimpose 2 ints by using a variant, whereas you can do that with a union. Before I go on, another thing I don't have a slide for, but it's quite important. Be sure and squeeze all the air out of your objects too, meaning order them by size, so that the compiler doesn't put in a bunch of padding bytes. we saw really, this morning's talk by Arthur was, had a great example of that, where he had this tremendous speed increase because he just got something a little bit smaller, and it ended up fitting in the cache. So now I'm going to talk about passing things around, because, I mean, one of the reasons I wanted to do this talk was that I'm always asking myself, you know, how do I pass this? How do I get this back from a function? What's going to be most efficient? I wasn't sure of the answers. So here's some of the answers. Pass simple things by value. Value semantics are a good thing. Anyway, C++ has all kinds of great support for value semantics. But remember that you're making a copy, and sometimes a copy is expensive. If you need a copy anyway, then it costs nothing. Pass by value. Generally speaking, we pass other things by const reference. Even shared pointer. So Nico had a great talk here, I forget what year it was, 3 years ago maybe, where he pointed out that passing shared pointer by reference when all you want to do is read it is a lot faster than passing it by value, which is kind of the natural thing to do. So pass by const reference. Also, if you're writing generic code and you want to know, okay, how should I take this parameter? Take it by const reference. It doesn't matter if it's a built-in type. It'll be just as fast. I measured this. It's just as fast. There's no penalty if you're passing an int and you're taking it by const reference. Not a problem. But of course, you know, all the usual caveats. With a reference, you have to be concerned about lifetime and what. And there's some efficiency considerations, so watch Nico's presentation. Now, I know that your mother told you not to speak to strangers and not to pass things by non-const reference. It makes code much harder to understand, reason about. Depending on what it is that you're sending in, value semantics may be just fine. Move gives us a huge benefit depending on what your object's like. But sometimes it's necessary, and sometimes it's much more efficient. So I'm going to give you an example of when it's much more efficient. So here, all I want to do is, with this one vector, I'm going to go through a loop some number of times. And every time I'm going to clear it, I'm going to load some stuff into it. And down here, I didn't write any code, but I'm going to do something with it. And I'm going to come back and do it again. Lots of times. OK. So let's think about what happens the second time through. The first time through, you know, the vector, I'm passing it by value here, right? The first time through, it's empty. Nothing really happens. A bunch of allocations happen here. As it fills it up, it gets returned, right? It gets returned by value, which means, and we're going to talk about this in a little bit, but it means that it's going to have the RVO, so there won't be any particular cost to that. All good, right? What happens the second time through? The second time through, what happens here? Thoughts? Questions? Anyone? Let's look. The second time through, the size is 1,000, right? And the capacity on this thing, or whatever I did it on, happens to be 1066, the library I was using. So we do a clear. The size is 0. The capacity is 1066, right? We call load numbers. We do a copy constructor, right? Now what happens? Size is 0, right? We didn't move anything. There aren't anything out there. But the capacity is 0, right? Because I've constructed a new one with an empty one. I'm not going to get that capacity, right? It's not going to do any allocation until I actually do something with it. And I have my whatever 10 allocations again. Every time through the loop, I'm going to do all those allocations. This is going to go super slow. So let's pass it by universal ref. That's not the right word anymore. It's forwarding reference?
It's not a forwarding ref because there's no type deduction. It's literally an R-value reference.
Right.
Function template to be the universal ref.
Yeah, right, exactly. I get those confused. So we're going to move it here, right? We're going to take simple R value reference. So what happens? So this fixes it, right? Sure, no problem. We move it here, and there's no constructor at all happening here. Right, we got our capacity, we fill it up, 0 allocations, all good. Is there a problem here? Anyone notice anything?
We're now returning the R-value reference that came in, so there's no RVO kicking in on the return.
That's true, but it's worse than that. This number's not the same. What happened to our 1066? Now it's 1,000. That's because it got returned by a copy constructor, which is kind of what you're saying. But not only did we not get the RVO, we did not get automatic move here. So we're copying it every time. Still pretty slow. Not as slow, but still pretty slow. So what can we do about this? Well, we have to do the move explicitly. And now we have no RVO. We have 2 moves, here and here. But we have 0 allocations and 0 copies, so we're doing pretty good. Can we do better? That's pretty good. I mean, notice we got our capacity back where it should be. What happens if we pass it by good old-fashioned non-const ref? Well, thoughts? Well, when we pass it, nothing happens. The size is what it is. The capacity is what it is. No allocations occur. When we return, nothing happens because there is no return statement. All right? This is fully optimal. We're not paying for moves. We're not paying for anything. So it doesn't get better than this. So for situations like this, passing by non-const ref, it's a good thing, even though your mother said not to.
That's why some folks have the convention do pass by pointer here to indicate that's what you're doing.
Fair enough. Myself, I'd pass by non-const ref before pointer, but that's, I mean, that eliminates certain
Same
problems.
purpose.
Yeah, it does the same thing. All right, so how do we return? So return by value, unless you're writing an accessor, you're going to get copyolision, return value optimization, in many circumstances. I'm assuming everyone knows what that is, but just briefly, it means that nothing happens at all because the object that you're actually working on in the function is the object at the call site. And this is mandated, actually mandated in C++17, I believe, under certain circumstances. If copyolision does not occur, then an automatic move may occur. Basically what happens is the compiler tries returning the expression as an R value. And if it can't, it returns it as an L value. But an RVO is better than a move because with the RVO, nothing happens. The move actually has to do the move. So there's some rules here. Don't do a move in your return statement. You notice I had to do that before to get it to do it. But if you do, you will inhibit the copyolision, so don't do it if you don't have to. The function return type's got to be exactly the same type as the type you're returning. or it can be a local variable. Excuse me, or a by-value parameter. If you have multiple return statements, that will often inhibit the RVO. I gather that's because it's hard to implement. So it's going to depend on your compiler. I don't know the data of what compiler does what here. But multiple return statements will not stop the automatic move from happening. Conditional expressions, on the other hand, will often prevent the automatic move. So either do one of these. Okay? Don't do this without the moves. So here's some examples of good return statements. All of these are going to be fine. And here's some examples of bad return statements. These all have the potential to inhibit your efficiency. Questions? I'm going fast, so hoping not to run out of time too badly.
Is there any transformation you can make to the third one that would be bad?
The third one.
Are you
No.
pass by constrep?
No,
Pass by constrep has already doomed you to be bad.
it's doomed you, yeah. I mean, you could do an explicit move. No, you can't. You can't. You can't. You're doomed. Yeah. Yeah. Yep. Maybe really what you wanted to do is pass by non-constref. I'm assuming everyone knows quite a lot about moving, so I'm not going to belabor moving. Right? Anyone want me to spend time on move? The main issue is coming up. Move semantics solves a whole lot of problems and makes a lot of code go a lot faster because you're not actually copying stuff around that you don't need to be. Works very well. However, there's lots of objects that absolutely move semantics do nothing for. And it's very easy, I've found, to say, oh, well, it'll be fine because we've got move. Well, it'll only be fine because of move if your objects manage resources. But if your objects just contain resources, which is what you want them to do in general, as we talked about earlier, you want to embed things in your objects to make them smaller and to limit allocations. Well, those objects are not going to get no benefit from moving at all. The contact object that we talked about, moving and copying are the same thing. Okay? A standard string is the same thing if it contains 15 characters or less in most libraries. Right? Because the standard string has a short string optimization, which is great. And the cost of copying the string when it's 15 characters is the same as the cost of doing a move. Okay? I measured this. It's the same cost. But it's still a cost. And if you're doing a whole lot of them, that cost might matter. I threw this in here mostly to get you to watch Howard's discussion of move. Oops, sorry, wrong button. In fact, if you take away nothing from this talk but the resolution to go watch Howard's talk and Nico's talk, fine. They're great. The big thing here is you often don't need to write any of these because they get written for you and they're often correct. All right. Let's look at an interesting case of doing a move. So, what's happening here? Is this good, bad, indifferent? Anyone? Boy, Is everyone asleep? What's going on here is that you're getting a copy. That's what pushback does. Pushback takes a const ref, and it's going to do a copy of this string. And let's say this is your latest Russian novel that just happens to begin with "Hello World." You're going to copy all of that. So that's not so good. So let's fix it. Does this fix it? Sure, right? In place is great, right? That fixes it. Does this fix it? This is exactly the same code. In fact, if you step in to the library that I use, you'll find that pushback calls in place back. Okay? So why doesn't this fix it? Well, because in place back's just calling that same constructor. What about this? Does this fix it? Question? Yes? No? Yes. What's that?
As well as it can for this code?
I think as well as it can for this code. Now we're going to get a move. Of course, down here, if you look at S, you're going to be in trouble, right? So this isn't necessarily ideal, but this is pretty good. We've gotten rid of the copy. We aren't copying your Russian novel anymore. Okay. What about this situation, though? You've decided that instead you're writing a very short poem. Well, does this help? No, we just discussed that, right? It's a short string optimization. It's not going to go any slower than the code we just saw, even though the code we just saw had a Russian novel hanging off it. But it's not going to go any faster.
You don't know it's not going to go any slower. If you've got a crazy library that says, I'm going to clear it after move, it will go slower.
That's true.
And as far as I know, all the major implementations do that.
Ours doesn't.
Oh, well,
It's unspecified
Yeah.
state can be the value it used to have.
yeah.
Oh, you're saying that it's going to write a null.
Some libraries might
Right.
used to do
So
that.
so it might be slightly slower. Okay. So what do we do? Does this help? No? It's the same thing. Okay. I thought we could use in place to fix this somehow. Can we? Why, yes. Like this. This is how in place is meant to be used. Okay? We're going to construct the string in place in the first place with our initial piece. And then we're going to act on that particular string. And there's no other string involved. Alistair.
Which version of the C++ standard does that require?
17.
That requires 17. Only because of this here. You can do this, and you can do the same thing. It'll work just as well. It's just one more line of code, because you can't in place back prior to 17 did not return anything, and so you would have another line that says autoreference s equals v dot back, but that won't cost you anything. Thank you for pointing that out. Okay, questions? How about this situation? Well, is this okay? No, we're back in a similar situation here, because we now have to construct an R value, right? Which can be moved from, for sure, and will be, but the move is going to cost you something. Maybe more than you think. This does absolutely nothing because there were already R values. Move is just a cast R value. This, however, does exactly what you want. Okay? I have to take a little sidebar to talk about perfect. Actually, it's more than a little sidebar now, isn't it? Yes. I'm going to talk about perfect forwarding a little bit. This is a little bit different, but it still leads into a discussion of efficiency. In case you aren't sure, because it took me a long time to be sure. In fact, I think it was sometime last Tuesday. What standard forward actually does, it's used only in generic contexts, and it ensures that you retain the R valueness or L valueness of whatever you're passing down into another function. And you need to use this is now the correct use of the term, forwarding reference for this. So I want to look at a little case study of you actually using this. So I've got this foo, which I construct with some stuff, okay? And I want to call it with this. So what's the problem here? We just discussed this at length, right? What happens here? Inefficiency, right? Same inefficiency we've just talked about. So what can we do to fix this? Well, it's actually pretty easy. You make this a template. You make this a forwarding reference. You call forward and pass that on to your string. And now this is fully efficient. This directly constructs the string in place, and all is well. Now let's look at a slightly more interesting situation. Supposing I have this class bar, and I want bar to have a vector of foos. So how should I write that? What's the best way to write that? Add. I want an add because I don't want to expose this to the public. But I do, the public knows that I hold foos, so the public wants to stick foos in. So this is my first attempt. Well, this is terrible for, the construction of the foo is good. We just fixed that. But now I'm going to copy the foo, right, entirely, including the string. I'm not going to get move to happen here. And the call site's really ugly. So my first thought is, okay, I can fix the call site by just doing this. I'll pass in the, what I want, and then I'll push back and I'll put the foo here. Well, that's nice. It cleans up the call site, but it's no more efficient. It's doing exactly the same thing. So I know I'll use modern C++. Does this help? No. This does exactly the same thing.
Only except this time it's an R value and you get a move. Also on the previous slide, I think.
Is it? No, I don't think so.
It constructs a temporary foo and then it moves it into a vector.
Oh. Yeah. Right. The thing is that foo doesn't implement move. String implements move, but foo doesn't.
Foo used rule of 6 to implement 0, therefore it's got the free move built in.
The string is small, so
That's true.
Yeah.
So you would get, that is true. You are getting the free move. Good point. So
Free move of a short string.
free move of a short string, which isn't free. Good point. Yes?
A couple of slides back, the constructor of foo.
This one?
Yes. Is that okay that we have local variable s and parameter s? Will that everything work okay?
Oh, yeah. So this is something I do. I don't know if I should, but I do it for very simple. I almost always name my member variables with an m underscore so I can tell they're members, unless it's a really simple struct where it just seems pointless. Like my point doesn't say m underscore x, m underscore y. It just says x, y. And when I do that, I actually do this because, yes, you can. It's totally legal. And in my way of thinking, it's not, when it's something this simple, it's not confusing. But one could argue that easily the other way.
Now, I think I'll pass both time, but while the slide's up, do you have any concerns of code size for generating different instantiations for every different length a string literal here. Every time you pass an array of char, it's an array of char of different length.
That's true.
That's potentially generating a lot of overloads.
That is true. There's another problem with this, by the way. There's a subtle correctness problem here. What's that? Someone here surely can come up with this.
Well, I would say there's a conversion problem.
What?
SDR can be, as long as SDR is converted, it will compile.
That's right. The correctness problem is that we haven't constrained STR at all. And that's easy to do. Well, it's kind of easy to do today. Not that easy, but in this company, pretty easy. It's going to be way easier to do with C++20 when we can use a requires. But I'm just pointing that out. It's not germane to our conversation, but it is true. All right, so some good points here. So we do get the free move, but it's not really, I mean, remember, the string isn't the whole story here. We're moving some other stuff here, and these don't have move semantics. Okay, this is just byte copying. So, what do we do? Does this help?
Assuming foo stores it as a pointer to character and not as a std string.
Well, we know that it stores it as a std string, but
Then this one only accepts string literals then. So
well, that's true regardless of what foo does. Exactly. This only accepts string literals. Suddenly I broke my... What's that?
Or other const char star pointers.
That's right. It only accepts char star. It does not accept strings. So I just broke half my code. So what do we really want to do? Well, turns out it's the same. We want to do this. Well, no. That gets us right back to the same situation. In fact, what we want to do is this. Now, this suffers from the same correctness thing we just talked about, but that aside, this is really awesome because now, not only is this optimal from a runtime point of view, because we are calling the constructor directly with this, of foo, directly with this, in place. But now, when foo changes, gets some more constructors, adds some more parameters, got some default parameters, doesn't matter, bar doesn't change, it just works. Questions?
Question.
Yes?
In the call site of the previous slide, if the value, if the third argument q is replaced with some other value r, will that result in generation another template instantiation? Will that template
Yes.
parameter be
I see-
interpreted as a
Right.
integer type
Yeah.
parameter?
The question is, if we change this from a Q to an R, does that make another add get instantiated? The answer is no, because the type of quote R quote and the type of quote Q quote are the same, and this is a type parameter.
So it will be interpreted as a type parameter, not as a value parameter of the template.
That's correct. That's correct.
But the same does not count for bond and chains. Those are two different types.
That's right. Because they're different lengths, and that is true. If you were going to call this a bunch with a bunch of different ones of these, you may want to do something about that. But if you don't, I mean, if you don't really have that many literals, I mean, how many different length literals are you going to have, right? Before it starts to be some other way you're doing it.
I'm not sure why you made it a variadic template. In this case, wouldn't just a single parameter be correct or even more correct?
A single parameter of what type?
Why is it a variadic template? not
Oh,
a single
because I'm passing in 4 things.
Oh, for all of them. Okay, never mind. I was confused.
Well, because, and we don't want to construct a foo down
I'm
here.
just focusing on the string.
Yeah. Yeah. Other questions? Okay. Now, different topic. There's a reason why we have all of these different containers and why we'd like some more. They all have a purpose, and they all have different trade-offs between these three things: speed, space, and convenience. But it's really, really important to pick the right container for the job, and we're going to look at that in some detail. So the first question that really comes up is, when should I use vector, right? Actually, I'm going to claim that that's the wrong question. I think this is the better question. When shouldn't I use vector? It's the go-to container. The other containers can have vastly better performance, or sometimes vector won't work at all. We're going to talk about that. Or vastly greater convenience, and maybe performance just really doesn't matter. There are those situations. But start by analyzing whether vector is the right thing to use. So vector, why is it great? Contiguous memory, fastest traversal, random access, right? All of these things because it has contiguous memory. On the other hand, growth invalidates everything if it grows. But you don't have to have a vector grow. You can pre-reserve. If you either know how many things you have, or you know what is a number that's larger than how many things you're going to have, you can pre-reserve, and you won't get any thrashing, and you won't get any movement. So now all your references and iterators are never going to get invalidated. If you're trying to do large amounts of data, you cannot use a vector because it grows geometrically. If you've got 4 gigabytes of RAM and you've got a 2 gigabyte vector that's full and you want to add one integer to it, you cannot do that. So vector doesn't work for large things. Array is great. It's just like a C array, only cleaner, fancier. It's great when you want to embed something in your object. So how do I choose? Well, if the size isn't fixed, you kind of need to use vector. It'd be really nice if we had a vector that has a fixed capacity, but we don't yet. I personally use C arrays for very simple situations, following the principle that use the simplest tool for the job.
I have a strong preference for standard array, just because my mental model of when you pass by value, pass by reference, I don't get array decay kicking in. It jibes better with my reasoning for the language as a whole. So that's a convenience rule rather than...
And that's a very good point. I mean, that's a good argument against what I'm saying. And I go back and forth on this. I tend to use... if I have three numbers that I need access to in a function this, half a page long, I generally use a C array. But as soon as you start trucking in it, around your program, then that argument really starts to cut in. I'm sorry. Good point. Thank you. The question was, or the comment was, why that C array has pointer decay characteristics that are surprising and annoying, and that if you use standard array, you don't get that. So DEC is great. I really like DEC because DEC has clumps of contiguous memory, and that gives you pretty fast traversal, and you get random access. Growth invalidates only iterators, not your pointers and references. but it has linear growth, so you can use it for large amounts of data. On the other hand, if you have a small amount of data, DECs are very wasteful, and they're slower and much larger. So, simple rules, right? The thing is, the whole point of DEC is you can push to the front. It's faster to push to the front of a vector until your vector gets pretty large. So, other factors are more important.
Is this the time to ask what quantity we think of small and large, or is that coming?
The question was, what do I mean by small and large? That's coming. Yes, almost, not quite. List. What are lists for? They're node-based, so the overhead is very high. The locality of reference is terrible, right? Because you have to allocate a separate node for every single element, and they're all over the place. You get slow, or certainly slower traversal. You get no random access. On the other hand, they're perfectly stable. Growth anywhere never invalidates anything. And they have perfectly linear growth, like per element. So you can make them very large. On the other hand, they use up an awful lot of space per element. So, if your element is very large, then the overhead of the list is unimportant. But if your element is an int, the overhead of the list is quite important. If you have a small one, there's almost no good argument for them. So, vectors much, much smaller and much faster for anything up to, insertion anywhere in a vector is much faster until you get pretty large. And we're going to talk about that in a minute. A big reason to use list is when you can benefit from splicing. So, let's look at some numbers. What I did here, this fine print basically says, this is for when you read the slides later, is that I created 10 million. I had a table of 10 million things I used to map. That's not involved in the discussion. My thingies had a list. I'm going to call it a list. It had a container that contained some elements, and I implemented that 3 ways: list, dec, and vector. When the container size for each of my elements of the larger thing was 10, and I had 10 million of them, look at the times. This is the time spent. What I did was I pushed, I pushed them into the front of the list, and then I removed them from the front of the list. Okay? So worst case for vector. And look at the numbers. Vector blew everybody away. Incrementally so over dec, but way faster than list. And look at this memory used by all this. Okay? So list is just way better. There's no argument. Vector is way better, no argument. I went up to 100, okay? Dec has pulled ahead speed-wise, but look at the memory usage. So okay, it's a little faster to use a dec, but do I really want to expend that much more memory? Depends on your situation. List is still way behind. Now, when I make the interior container 1,000, well, I didn't use list at all because that just ran too slowly to measure in this situation. Because I had 100K of them, and I wanted to keep the numbers in the same ballpark. Dec is now, really, really fast, And vector is now quite a lot slower, but it's still a lot smaller. Questions? Set and map. So this slide should look familiar. It's the same slide as for list. Same principles apply. They're nodes. It's a node-based container. It's just a matter of how you hook them up. Whoops. So arbitrary insertion is faster until the size is quite large. This shouldn't be surprising at this point. Maintaining order is faster until the size is quite large, if you need to maintain order. Binary search on vector works just as well as searching in a tree. In fact, it's probably faster. For small containers, linear search is faster than binary search. You don't need to keep it in order if all you're doing is going to find it. It's actually faster to do a linear search. So let's look at how I tested this. So I created an element that was going to keep a set of integers conceptually. So a unique ordered list of integers. And I said, okay, that's what I need in this thing. And I threw in something else just to make it somewhat realistic. And I implemented this two ways. This is one way. This is the other way. They work identically. The only difference is that this uses a vector, and I wrote this probably fairly dumb insert that just does a ordered insert. Okay? And then I ran the comparison. So again, at 10 million objects of size 10, vector's faster and way smaller. Now mind you, what it says here in the fine print is that I put the elements in backwards so that it was worst case for vector. Again, the vector had to slide. I put them in and then I put them in again. And in the first case, the vector had to slide every time. It never got the advantage of, oh, it goes in the end. It had to actually make room every time. So worst case for vector. At 100, well, vector's even I mean, there's, a tenth as many of them, but vector is, the improvement of vector over set is more at size 100. I would have thought that, it would get worse and worse. No, it's actually more so at size 100, and far more savings. Once we get to 1,000, vector is now behind set in terms of time, but I mean, look at the memory usage. And it's not way behind, right? It's just incrementally slower. Does this all make sense? Questions? Yeah.
I think inserting everything in reverse order is also a poor case for set because the amount of rebalancing it's going to do, but just not as bad as for vector.
It's not as bad, right. I wanted to make it worst for vector. Yeah, that's a good point. So, theorem 3, right? Use vector. Except, of course, when it's not the right choice. My real point is you have to make this choice every time.
Is now the time to talk about containers where order doesn't matter?
Sure.
We again looked at using sorted vectors for our lookup, trying to do a flat set at Bloomberg a while back, because we're having trouble with our looking at sets of strings. And it was pointed out that with benchmarking, our hash function for strings was quite bad, and the right answer was actually hash set once we tuned our hash function.
Okay, so the
So unordered containers are often a better answer than a sorted vector for lookup.
interesting.
If
So
order doesn't matter.
okay. So the comment was that under some circumstances with a good hash function, an unordered map, hash map of some sort, but presumably you mean the standard one,
If you're looking for just an associative lookup,
yeah, and if you don't care about order, is even better than vector.
Yes.
I'd be interested to see if that's true as the size gets small, because the overhead of that is going to be tremendous for small containers, right? I mean,
I can't remember
relative.
what that, we had benchmarks, and yeah, they definitely come. There are more effects there. I can't remember
Yeah.
what the exact trade-off was.
I didn't include the unordered maps, and I probably should have, because they're definitely different. But I think that this gets the point across, which is for every use, you need to evaluate which is the correct container for this situation. Not every other situation is different. It's always.
The performance benchmarks vary significantly if you went, are we inserting and erasing during the lifetime versus populating up front? Does the data come in ordered and so forth?
Yeah.
Benchmark your specific concern if you're tuning it.
Right. See if I can paraphrase that. You're saying be sure and benchmark exactly what you're doing.
The set of operations over your data.
The set of operations, yeah, because something different is going to behave differently. Yeah. Okay. So now we come to the spiritual portion of the talk. We're going to have a little Eastern philosophy here, and we're going to talk about how you can move even faster by not moving at all. So we've already seen that objects may not get any benefit from being moved, right? Moving is just as expensive as copying. Furthermore, construction and destruction may have side effects that you don't want to repeat. If your object launches a rocket in its constructor and blows it up in its destructor, you probably don't want an accidental copy in there. That might not go well. And that can be true of things that are less dramatic, right? Like a database connection. And you may want objects to be stable. In fact, some objects want to be permanently stable for their entire lifetime. Okay? Node-based containers are stable. Vectors can be used in a stable way, but you need to get things into them and out of them. Okay? And sometimes esoteric examples aren't necessary. Sometimes you have a simple little object. It's got 128 bytes. It's your contact object. It's got a couple of phone numbers and whatever. But you've got zillions of them. So it's just too expensive to mess around constructing, destructing, copying, et cetera, et cetera. So, and this is somewhat repeating things that I've already said, but basically you want to use in place to construct things in place so that they never have to move or copy. Okay? Here's some reasons why you'd use in place. This is one of my favorite little idioms. Okay? And yes, you can do this in C++ 14 and earlier with 2 lines of code, but I really like it now. I've got my vector, let's say. I call him place back. I'm asking for the default constructor because I don't want it to have anything because I'm about to read it from a file. I just call read. I pass it the file object. Boom. I've just read element number 1. When not to use it.
Constructor might also be expensive, right?
The question was that the default constructor might also be expensive? Sure. But it's hard to imagine how you would, well, absolutely. So there's a reason I use this, but you also, another idiom that would solve that problem is to have this is assuming that there isn't a constructor, a read constructor on the object. But if there's a read constructor on the object, you just take this read and a couple of parentheses out, and you call in place back with the file object, and you've eliminated that problem. Good question. When not to use in place? Well, if it's a copy anyway, like for built-in types, principle of using the simplest tool for the job says use push back, not in place. There's another little more subtle one. If you want to ensure that explicit constructors are not called, If you call pushback, you will ensure that. If you call emplace back, it will call explicit instructors, because that's what you're doing, is calling the constructors of the object. Alistair.
I'm not sure I buy the when it's a copy anyway to not use emplace, just because you're doubling your vocabulary for a special case that you have to know more about. If you expect the copy to be as efficient when you emplace, it's simpler to have just one way of doing things.
Okay, so
The
they,
second concern is real.
yeah. So Alistair's comment was that you could argue the simplest tool for the job the other way and say that it's simpler to call emplace back because then that's what you always use. And you don't have to think about, well, should I be calling pushback or emplace back? How simple is simple? You just always use that. And it's not, as we've seen, it's not going to matter at runtime because it's going to call emplace back anyway.
Depending on the type in the container, though, in-place back or in-place functions may not actually be an option. For example, with aggregate types, you have to construct the temporary using aggregate initialization, then pass it to pushback. It doesn't work with in-place back, and you would be getting no benefit from using it.
So the question, the comment was that with aggregate construction, you mean with braces?
Yes.
Yeah, with aggregate,
Types.
yeah, with aggregate construction, you can't call emplace back. I don't know about that. Is that true? Does anyone else? I mean, why is that?
In-place back is specified to use direct non-list initialization when constructing the in-place object, which means it's using parentheses. So if you're trying to initialize an aggregate type,
I think
it
you,
will fail because you need to use curly braces to initialize aggregate types.
But you can initialize aggregate type as a template, and then you get a move or
yeah. Okay, that's interesting. So aggregate, the comment was that aggregate types require a curly brace initializer and that gets lost in the process of passing it down through and place back to the
It's a
constructor.
non-reduced context.
Right,
It doesn't work when there's perfect forwarding.
yeah. He said it's a non-deduced context. Alistair.
And we're still talking about fixing that for C++20. The two cases it will work are when you go for the default value initialization, so you pass no parameters, or it's a copy. So it will work in two very special cases, but pushback is
Right.
one of those.
Okay, so Alistair says that it's maybe going to get fixed for 20. And the other thing was that it works now in certain special
It will work
cases.
if you've got no parameters, so your value initialization, your aggregate will actually be constructed correctly.
Right, okay.
And if it's exactly a copy, because we put special rules into 14 to fix that case.
Okay, interesting. I don't do much with, other than to just use them, I don't do much with aggregate initialization myself. All right. So now let's talk about splicing. Here's another way of not moving or copying. Things stay put. Everyone knows what splicing is, right? Lists have a splice method. In fact, it's one of the few reasons to use list is that you can splice it. Nothing's invalidated. It's super fast. You're just twiddling pointers. All right, we all know this, right? You go from here to here. Okay. Until C++17, there's nothing, you couldn't do anything like this to a map or a set. All right. And furthermore, you couldn't change the key of an element. Anything like that you wanted to do, you had to create new elements, delete old elements, construction, copying, all this stuff we're trying to avoid. With C++17, we have node extraction. With node extraction, you can do all these things and more. You can change the key of an element, you can transfer elements around, even between maps and multi-maps. you can merge one container into the other. You can take an element out and hold it for later use. I'm going to show an interesting example of this. And you can move an element out of a set. I actually didn't realize this until very recently, but until node extraction, you could put move-only elements into a set and then presumably observe them there, but you couldn't move them out of the set, which seems like a major problem. So let's look at how node extraction works. Let's say you want to change the key of an element, and all the other things sort of follow the same pattern. So let's say we want to change this guy from X to Y. Well, what we do is we remove it from, we extract it from the map or set, from the container, and we hold on to it with a node handle. Then we can change the value because it's no longer a member of the container. You see, it's not the same color anymore. So we can change the key without messing up the container. The container's happy, it doesn't have that element anymore. And now we can put it back in. You'll notice the element never moved in memory. All we did was twiddle the pointers and change the key value. So what's the code look like for this? Well, it's awfully simple. Here's my map. All right. I call extract, pass it a value or an iterator. And I get this node handle thing, which we have to use auto for because it's one of these, secret library types. It's not secret, it's in the standard, but it's nothing that you really want to mess with. But you do want to use its API to access the key. It gives you a non-const accessor for the key. Don't inquire too hard as to how that happens. And then you just call insert. Now this node handle thing is a move-only type, right? For good reason. You wouldn't want to make a copy of it. That's the whole point, is that you're trying to move this thing and not copy it, you're trying to transfer this thing, I want to watch my terminology, without moving it or copying it. So you can't copy it, but you can move it. Move the node handle, mind you. No move happens to the element. And you just call insert with this thing, and you're done. And of course, if your code is such that this all happens in a R-value context, then you don't even have to call move. Another example, let's say I want to merge these two sets. Well, that's one line of code. Just call merge. Notice what happened here, right? It's a set, not a multi-set, and there's two 5s here. So we're merging source into destination. When we're done, we get destination with all of source except that extra 5, and that's left in source. So no element ever gets dropped on the floor. If you attempt to insert a node handle and it doesn't work, the insert returns an extra parameter that is a node handle of the thing that didn't get inserted, so it doesn't get dropped on the floor. Now, if you ignore it, it'll get destructed by the destructor of the node handle. And by the way, that'll happen using the correct allocator, a copy of your allocator. But nothing's ever dropped on the floor unless you want it to be. You also can use this is a slightly more interesting example here, to make incredibly efficient factories. Now sometimes, it's great to be able to place things in place, but sometimes a factory is really a pattern that you want to use. So how do we make an efficient factory? So this factory function takes a char star, and it's going to create a new record in my map of int and string, right? And it's going to manage the ID for me. So that's why I want a factory here, okay? So how do I do that? Well, down here I just call insert new record with whatever, and it just works. So how does that work? There's a temporary map. I'm going to emplace the thing into the temporary map, so that's fully efficient. Constructs it once in the temporary map. I'm then going to extract that node and return the node handle. Notice it says auto here. Okay. And that's now here is going to be an R value, so I can directly insert it into my new table, and all it does is fiddle with the pointers. The thing in memory never moves. And I think that's it. That's going to be it. Questions, discussion, thoughts?
Got a question.
Yeah.
So do you have any benchmark data for like concurrency examples? So, you know, if I want to spawn up a bunch of threads to do work like in parallel, like would these still apply, or would I need to use different containers in those circumstances?
So, the really short answer is I don't know, because I'm not a concurrency expert by any stretch of the imagination. So concurrency, I took a slide out where I was going to talk about this, but there's a lot of ways to get speed with modern computers, modern programming. Probably the single most important is concurrency, right? We have multiple processors. We need to keep them busy. That's a whole topic on its own. I'm not the person to talk about it. And when you talk about concurrent containers, I don't know how those stack up. This is how you write individual threads and make them fast. So one of the things that I didn't mention earlier, give me a minute, I have to bring it back. Any other questions while I'm thinking of what I was going to say? Yes?
Another random observation of micro-optimizations that people often miss is with shared pointer, you were talking about passing by const reference and so forth to avoid the cost of copies. Moving shared pointers, because you're avoiding a couple of increments on atomic variables, is often very useful.
Okay, moving.
Big atomics just can be flushing
Yeah.
cache lines and messing your caches in subtle ways.
So his comment was that moving shared pointers can really improve your concurrency performance
It can
characteristics.
Yeah.
Yeah. So what I was going to say is that what the whole point of this talk is to say that writing efficient code isn't just for people who work for, national laboratories, or that guy down the hall who never opens his blinds and has a editor that's green on black. It's for everybody all the time. I like to always be thinking about, is the code I'm writing optimal and efficient? And when you do that, you end up, after you've written a big program, with a big program that runs fast, and is correct, and you don't have to worry about going back and tuning it, unless you run into one of those situations where it's spending a whole bunch of its time in one little spot.
And the other observation, efficient isn't just fast, it's energy efficient, and that's a big thing these days.
Oh.
Small devices and large data centers.
Alistair's point is a very good one. Efficient isn't just fast, it's energy efficient. I learned something, this was some years ago now, that really surprised me. And there's people in the room who I'm sure can talk about this all day, but the cost of a typical computer over its lifetime is something like, at the time it was something like 25% the equipment and 75% the power to run it for its lifetime. I mean, the cost of power is huge, and if you don't need as much computing power, right? If you don't need as much memory, all these things cost money. And if you can run it for less time to get a certain amount of work done, you're saving money. Other questions, thoughts, comments, suggestions? I know everyone's thinking beer and hot dogs.
Can you share the PDF on Slack?
I'm sorry?
Can you share the PDF on Slack on the Slack tab?
I can, except I have been unable to get invited to the Slack channel. It's been blocked and not working.
Okay.
But I'm sure that the slides are going to be made available, I'm pretty sure that the video is going to be made available. So it will be available. Sure.
Perhaps the string parameter should be a forwarding reference, a templated forward reference.
Are you talking about new record?
Since it's in place constructing the string within the map.
Sure, if I wanted it to take something other than a char star. Right. Oh, you're saying in this actual code?
Yes.
Okay. So the question was, should this be a forward, right?
And new record be changed into a template function with a forwarding
Okay.
reference string
So-
argument
So
that forwards it down to the in-place call.
So you're saying change the new record to be able to take more than just a char star.
Yeah.
And in which case we would want to, if we're going to make it a template, we'd want to perfect forward whatever came into the M place.
Since the target type is a string, so
That's correct. I wrote this to show something else, so I wasn't really worried about that. But if we wanted this to be more universal, we would want to do that for sure.
And we would break the code because you now have multiple static ints having separate counts.
Yes, you're right. That's a very good point. The way this is implemented, this particular, which you'd hopefully never do like this. Or maybe that would be exactly so Alistair's point was that as soon as you start making more of these, because it's a template, every single one of them has its own static int ID. So its own ID starting from 0. And since they're all going in the same place, that's almost certainly wrong. Yes?
I think you'd also, if you fix that and you made global ID, I think you'd also have to use piecewise construct there, because there's multiple string constructors that can take more than one parameter.
So the question, the comment was that you would have to use piecewise construct here in the in-place call.
If you use a variadic.
If you use a variadic. That's a really interesting comment. I don't know the answer. I would have thought not. I would hope not. I hate that anyway a lot. But it wasn't the original design. It may be the case, and I don't know the answer. I don't know if anyone's compiler in their head can do that.
as is, it should be okay. If you were forwarding more than one argument to the constructor of the stood string, then you would need to use
That's right.
piecewise.
That's definitely true. If there's more than 2 things here, you're definitely going to have to use it.
As is, though, I believe it will just
Yeah.
use it, convert.
Because you're not going to make this a variadic, right? You're going to make this to take a single string template parameter. Right.
That's the problem with the static.
Other questions, comments, thoughts? Does anyone? I have a question. Okay, I'm sorry. Go ahead.
You suggested in the very beginning we throw stuff at you for saying optimize everything. So I'm at least going to throw this comment now.
Yes. Okay.
Optimize everything gets junior programmers carried away very often. And I don't believe what you showed was optimize everything. It was don't pessimize at all. So maybe that's a better summary for this whole talk than optimize everything.
I like that very much. Thank you. So the comment was, instead of saying optimize everything or write everything optimally, the topic really should have been don't pessimize at all anywhere. I agree. I mean, I think it's somewhat a matter of semantics, but it's a good way to think about it. right? It's like if it doesn't matter, or if if you're writing code where it just doesn't matter, how the normal way to write it can't be improved on, which is lots of code, or you're in a situation where it really genuinely doesn't matter. And I'm going to say like user interfaces, but then I'm going to remind you of my opening story. Typing is a user interface phenomenon, right? So it's not always true that user interfaces, it doesn't matter. Then just write normal code. But when you are in a situation where it could matter, or where you're doing something where how you write it matters, be sure you're not pessimizing at all. Yeah, I agree. That's excellent. I had a question. Does anyone disagree that we need to think about these things and that there's some sort of a problem with a 1,000 times faster computer not keeping up with typing that a 1,000 times slower computer could keep up with? Even given that it's doing lots of other stuff. I know there's a lot of fluff in there, but 1,000 times. Does anyone disagree?
Well, I'm not disagreeing, but I think that we need to get the OS driver developers in this room here.
Okay, the comment was we need OS driver developers in the room to hear these things. Fair enough. There's a lot of factors, absolutely. But I've certainly run into a lot of the kind of thinking. Hello? Oh, did someone turn?
People could come up.
Why did it do that?
Yeah.
Oh, there we go. Thank you. I've run into a lot of attitude that it just doesn't matter. I mean, not to pick on Java, but I'd love to pick on Java. In Java, and I'm not a Java expert, so tell me if I'm incorrect, but in Java you've got little int and big int, right? And they're very fundamentally different. But all of your user-defined types are like big int. They all are objects, which means they're all dynamically allocated. So you can't embed things. You can't embed one user object in another directly. And that just has humongous space and time implications. And I was involved in a project some years ago now where that was really, they tried to do a big data project in Java and it failed miserably. And that I'm pretty sure, I'm pretty convinced that that kind of thing was a lot of the reason.
That is why Java emphasizes different design patterns. We use flyweight a lot more in Java, where you can start using object identity to avoid having these clones and things for this kind of reason.
Yeah.
So, use the idioms of the language. I'm not sure how much that helps overall in Java. I don't do a lot of Java, but I know that you approach design differently in that environment.
The comment was, use the design patterns that work for the language you're using, which is certainly a wise thing to say. But I think that in C++, using the correct design idioms, you end up with code that can't be improved on particularly, even if you were writing an assembly code. And that's the whole point of C++, right? So it is exactly 6 o'clock. Any other questions, comments? Thank you.